we're going to use is 37%.
The HCl? Yeah, that's constant. It's like 12.1 molar.
There's a theme for this class.
Titration.
Last week was let the titrations begin. This week it is let the titrations continue.
Wow, that's exciting.
Isn't that exciting?
Yeah.
So today's lab is actually part of a multi-week lab. Now, I'm going to ask that you write 2 conclusions in your laboratory notebook. We'll turn those in together. So this lab will not be due next week. Okay? We're actually preparing our own solutions of standardized acid or base. Okay? And so I'm going to have you guys split into partners. Okay? Yeah. And one of you is going to standardize an acid today, and the other is going to standardize a base, a liter of each of those. Okay? And then next week we'll put out unknowns. And one of you will titrate the acid unknown, and one of you will titrate the base unknown using pH probe. And so then we're going to learn some technique, and I'll decide when I'm going to do that spreadsheet. I have a practice spreadsheet that I can show you, or I can even pull it up today, where we're going to use math derivatives to find the endpoints. Okay, so it's an alternate way to find an endpoint. Cool? You guys with me? And so we're going to learn how to do that. So, that's not the right one. Is it? No. Let me see if I flip those. Try to go to the new slide, right? Yes. Yeah, it is. All right. Okay. So, anyway, just a reminder, you guys know what a titration is, but I put this up. It's a form of volumetric analysis. And we use increments of 2 reagents, a reaction, right, to find an endpoint. Now, these get complex. We're going to do some titrations later on this year where we actually do a precipitation reaction, for example, and get that to precipitate. Or we'll do places where we actually do things like we titrate past the point and then back to the end point. Or we titrate one species and then use stoichiometry to figure out what the concentration of the other species is. And so all of these relationships are done, but we basically have to have a reaction, and whatever it is we're titrating should be used up in the process. Okay, that's really the big part to kind of get into that. We're doing acid base today, but we can do many other things, and we will by the end of the semester. This is the actual reaction that we're doing today, or the reactions. We're doing one where we're taking our sodium hydroxide solution that we prepare, and we're reacting it with potassium hydrogen phthalate. Now I have a question. What's the sodium hydroxide reacting with in this? In the potassium hydrogen phthalate?
The hydrogen hydroxide acid.
The hydrogen right there, yeah. So that is an acidic proton. Now, this is chosen because it's called a primary standard, right? And we've talked about primary standards being very stable compounds. They don't fall apart. They're easy to weigh. Sometimes when you dry them, they melt, but not always. When you're too hot. That was kind of funny. But anyway, so if we're looking at that, then it's deprotonated, and we make water as our endpoint. Now, as our product. The endpoint, how do we find the endpoint in this? What are you doing today? Phenolphthalein. So phenolphthalein in the basic solution is what color?
Pink. Well, it's
So what do you start with in your burette in today's lab? Yeah, what's in the burette? Sodium hydroxide. So what's in the flask?
Water and
What in, and then you put phenolphthalein in there, and what do you see? It's clear, nothing happens, right? So in base, it's pink.
Yeah.
So when I start adding base, when it becomes basic, then it deprotonates, and it deprotonates the phenolphthalein in the same fashion because phenolphthalein is a weak acid, right? And so when it deprotonates, it changes from clear to pink. So structural change. Cool? You guys with me? And then we do the same thing down here, except we're using bromocriso green. Yeah. And so we'll see a color change associated with that. So this is our HCl. You're going to make that solution from 37%. Yep.
Sorry to interrupt, but
No,
your
you're good.
phenolphthalein, if it deprotonates the phenolphthalein,
Mhm.
then how does that not affect your molarity calculation?
Because it happens after the other one. And it's in such low concentration. If you put too much indicator in, then it can affect an acid-base acid-base reaction that you're trying to look at and use it as an indicator. Does that make sense? Yep. So acid and base indicators are all weak acids and weak bases themselves. And they have about a 2-unit pH range where they change colors. And so that's where if you were titrating them, you would find that endpoint. Does that make sense? Yep. All right, they just happen to have color to them, which make them convenient to use. All right, so it's chemistry. You can use a stir bar today if you would like, or I kind of like to swirl. I like an Erlenmeyer's made to swirl, and as I'm titrating, I like to swirl and do it that way. But either way, whatever's convenient for you. Does that make sense? So whatever you're comfortable with. But that's the typical setup and reaction point. Now, you guys know that there's a difference between the equivalence point, right? The equivalence point is where the ideal endpoint, where stoichiometry comes to play and we use up all of one of the reactants, okay? The one that we're trying to titrate. And that's the ideal place. But in reality, we measure endpoints most often. And those endpoints come from a change of color in an indicator, right? Or if we're doing a titration curve like we're going to be doing next week, and we start basic and we titrate an acid into that, and that endpoint is at that position in the middle of those two curves, okay? Now the weaker that system is, then we'll see that compress, okay? And the stronger it is, then they'll see a bigger separation there, yeah.
So where would the equivalence point be? So if the endpoint's like right in the middle of the curve, like where?
Well, that's actually where the equivalence point is too in a curve,
Okay.
okay? Theoretically, that's where we would meet that. That's where we are starting to bend the opposite direction, okay? So that's where we're at pH 7 if we're doing acid and base. And so there's equal amounts of OH minus and H plus present at that point if we're doing strong acid, strong base.
So we see the endpoint though when it starts to get like slightly basic.
Yeah, so indicators actually, like if I were doing this titration, generally the ones we use change right in here.
So it's not quite the equivalence point.
So it's not quite the equivalence
I
one,
see.
but we still get a good endpoint,
Right.
okay? And because, especially because this is, if your titration is set up right, this is a fraction of a drop from here to here. Yep. Cool? All right. So anyway, so that's what this is talking about in terms of that. Methods for determining endpoints, which we've already been discussing. Electrodes, pH electrode is one of those. We're actually going to build our own electrode later on in the semester to do a precipitation titration. So you guys will get to solder and put solution in it and fill it yourself. Hook it up to a potentiostat to observe your titration change. So it's kind of fun. So there's more to it than just the titration, right? And so anyway, we can even use spectrometers to monitor the end of titrations. And in fact, there are auto titrators in the world that, as an analyst, usually they're used in situations where a person is doing quality control, those types of things, quality control, quality assurance, and they run a lot of samples every day. And so all they do is make the reagents, fill the either that or plug in the bottle of reagent that they've made and push start, and the sample will dump in from one side and it will titrate it, and then it'll do the next one, and it's all robotic and rotate that wheel, and you just can run multiple titrations through, and it does all the own detection with either light and then it counts the amount by drop counter or other mechanism to get the volume. So cool. Yeah. Indicators is what we are going to use today, and then next week we're going to try a different endpoint. Now, we can define the difference between the endpoint and the equivalence point as a titration error, and so we can actually do a blank titration sometimes to help correct for that. We're not doing that today, okay? So just to let you know that, or I don't believe that we are. I can't remember reading that when I read the lab. So,
Sodium chloride blank?
huh?
The sodium chloride blank?
Are we doing a sodium chloride blank?
It was in the lab.
Okay, then if that's the case, then yes. I don't remember reading that, so I read it about an hour ago, but I may have missed that because I was looking for something else that I was trying to verify. But anyway, so we are doing that today. So you guys know the lab better than I do. That's good. Validity of analytic results depend on the amount of one of the reactants. And so as we talked about that primary standard, this is just a list of things that we've talked about multiple times. So if you would like to look at that. So chemicals are sold under many grades. And so we actually want to use the primary standard grade when we're doing this for analysis, if you're doing this commercially or whatever that may be, and somebody depended on you. So just be aware of that. And so anyway, those are the highest quality. Many reagents used as titrants are not available as primary standards, such as HCl, okay? And so then we have to standardize that and then use that to compare to something else, and that's the process you're doing today. All right, so we are doing a standardization. This was just the other things that we talked about, the direct titration, back titration, gravimetric titration. All of those are things that we can do. And titration calculations. All right, you guys can do these already. I think you're well enough trained, and you guys had this sheet when you were in general chemistry, and this is the titration calculation sheet. You guys with me? If you start with grams of your standard, right? Then you can go to moles of your standard. You have the chemical reaction, it was on that second or third slide, and you can go from your moles of standard to moles of compound, and then from that, you're going to be looking at concentration. So we're going to write here, so we know the volume of that we had, and so then we can calculate that concentration. And so it's right here. Does that make sense? This sheet works for all of these, even back titrations to go forward and then backwards and so on. It just adds steps to it, okay? So you guys good with this? Yeah. So I have confidence in you that you are prepared to do this, all right? All right, just a couple things about this. This compound will eat you, okay? Do you understand what that says, or you guys understand what that says? Yeah, so if you get sodium hydroxide 50% on you, what should you do?
Rinse it off.
Immediately rinse with water, okay? I'm telling you that. This one down here, 37% HCl, if you get it in soft tissue, can be dangerous. Now, if you get it on your skin, you should still rinse it off, but it's not nearly as aggressive as the sodium hydroxide, which will start to convert your oils in your skin to soap, and then immediately start cutting your proteins up, okay? You with me? So just trying to say with that those two chemicals, when you're using 37% HCl or 50% sodium hydroxide, I want you to wear goggles, face shield, and a lab coat. Okay? So in that first step, everybody, when you're measuring those, I want you to use that. Cool? After that, you can just wear your safety glasses. Okay? So, but just in that first step. But I think that you guys are at a point where you should start to make solutions like this. Actually, most of you are lab assistants and you already do. Okay, but that's the appropriate protection, PPE that you should be wearing for those situations. Okay, so we're going to do that. And then once you get the solutions neutralized from the titration, they can go down the drain. All right, cool? All right, find a partner. Half of you prepare sodium hydroxide, half of you prepare the hydrochloric acid solutions and dilute them. Now, they're actually degassing. It says to heat your water down there, but if you heat your water, then you have to let it cool down before you make the solutions, or you should. And so what I did was I have them degassed by vacuum, and that water should be ready for you to go. So that first step, the water's degassed. Now, why are we degassing it? This is a good question. What gas is in there of concern? Anybody know?
Carbon dioxide.
Carbon dioxide, okay? Now, if you notice, it didn't say to degas the one for the HCl, right? Did you guys notice that? Well, that's because there's nothing that's going to react in the gas phase with the HCl, but the sodium hydroxide, what does it make when it reacts with CO2? Anybody know?
Na2CO3.
Na2CO3, sodium carbonate, right? And that will, and then if there's calcium present, then it will precipitate as calcium carbonate, right? You guys with me? And so then you'll notice sodium hydroxide solutions that have been sitting around a while, guess what? They'll have a solid on the bottom where those carbonates are precipitating out. Cool? Yeah. So that's why we're doing that. So you might ask that. All right. Any questions?
So if we're using the hydrochloric acid, we don't need to use the degas water.
You don't need to use the degas water. You can just use DI water.
Gotcha. And so when you're titrating, did I notice this as well? When you're titrating the sodium hydroxide, you still need to use degas water for your.
You should, otherwise if there's CO2 in there, then it will react during the titration and become part of that, and it will give you a titration error.
Gotcha.
Yep. Cool.
Yeah.
So degassing water, we actually have a student who degassed some yesterday, I think.
Yes.
Yeah. And so he's getting ready to do some HPLC. We have to degas for a different reason there. And the reason we degas for HPLC is under high pressures, the gases will be forced out of the solution and they make bubbles, and then those bubbles get in detectors and they cause weird signal. Okay? So we're degassing for a different reason. We don't want bubbles. Yep. Cool. All right. But you can boil, you can vacuum, and when we get the sonicator back again, you just throw it in the sonicator for 5 minutes, and that's the best way to do it. The quickest anyway.
It's easier.
It's here?
It's here. It's in the office. Just get in.
Good, we have a new sonicator, so I'm excited. All right,
Just needs to be set up.
that makes your life easier, Avery. All right, I'm done.